So I'm Jonathan Buonocore, I'm a research scientist at the Center for Climate, Health, and the Global Environment at the Harvard T.H. Chan School of Public Health. Most of my research either focuses on health benefits of climate mitigation or health impacts of energy. So today, we're going to talk about health impacts of energy and what we do and don't know about fossil gas and how it might affect health. Anything I missed in that introduction that I should go back and explain? Other than the fact that I'm working with you on some studies that we might make reference to in the next half hour or so. Perfect.
We're lucky to be associated with you.
I'm lucky, not you. I'm the lucky one. Okay, so this is the fossil gas supply chain going from left to right. You can see on the left side, there's the 4 steps of getting gas out of the ground, which is to find a place where there might be some, explore to find where it actually is, build yourself a well, and then do the production. Once you get whatever's in the ground out of the ground, you have to do some processing to it to pull out water, to separate gas from oil, to pull out sulfur, and then all kinds of other contaminants. From there, if it's not, if it's propane or butane or ethane or something like that, it goes in a pipeline to a fractionator where it gets split off to go become propane or ethane or plastic or whatever it is. The methane portion of it, which may or may not go to your stove, your heating, whatever else, also comes out of this processing plant, goes through liquefaction. Some of it goes to be exported, and if it gets liquefied, it gets compressed and uncompressed back to gas and goes back in the pipeline. Some of it just goes straight into a pipeline. From there, it goes into some kind of market hub. Because we use a lot more gas in the winter for heating than we do in the summer, and you can't really turn gas wells on and off over time, we end up putting somewhere between 10 and 20% of it back underground in places that are closer to cities and underground gas storage. If that sounds vaguely familiar to you, that's because one of these facilities happened to have a well blowout. Its name is Aliso Canyon. What was it, 10,000 people or so got evacuated when it blew out, and it was the largest single accidental release of methane in this country. We'll talk about that later on, but it gets pumped underground during what's called an injection season, which is usually the spring, and then it gets withdrawn from underground during heating season, so that flip is going to happen probably sometime next month. And gas then goes to your local gas company or to power plants or to industry. And from your local gas company, it goes to buildings, to residences, to be used for fuel and all the other kind of end uses for gas. So that's what the supply chain kind of looks like in abstract, going through all the different processes. It's pretty long. This is what it looks like in the United States. The kind of yellow and orange blotches are sort of the shale plays and the actively producing areas. Under that, each of the little brown and blue dots are active wells. The larger blue dots that have flames on them are all the power plants. Blue squares are processing plants. The white squares are those aforementioned facilities. And all the lines are either pipelines or railroads that happen to maybe carry oil. So there's a lot of natural gas infrastructure in this country, it turns out. This map will show up many, many times, so don't worry if it's a little bit of an eye test right now. This is your natural gas consumption. Having gone up over time in total, that is mostly driven by increasing production in the electrical sector, but maybe there's a little bit more going to transportation, going to industry and that kind of thing. Industry. But by and large, it's being driven by gas displacing coal. So, the questions we're going to talk about today are: what are possible health impacts that we can see all along the supply chain? What evidence do we have? And at the end of this, we're going to talk about what evidence is lacking. So we're going to start at the beginning of the supply chain of production, which is this whole left part here, everything between finding the well and initially pulling whatever's out of the ground. This is where production happens in the country. Again, the bluish gray dots are gas, the brownish ones are oil, and the splotches are shale plays or otherwise oil producing areas. This is what a natural gas play looks like in cross section. Your sort of conventional gas is trapped in usually what's called a cap rock here. This where it has this kind of inflection point where it's kind of like a saddle. Because gas is light, it tries to float to the surface of wherever it is, and then it gets stuck in these cap rocks. There's some kind of impermeable, like limestone or something. And where we have these little bubbles, we just drill underground and there's gas. Great, we can pull it out of the ground under its own pressure. The kind of boom in hydraulic fracturing in the last decade or so is largely driven by the well to the right of this, which is considered unconventional well. So rather than just drilling down to the gas that's easy to get, you drill down to usually shale and end up drilling downwards and then drilling sideways for a while, injecting a bunch of fluids and that kind of thing to break up the shale and pull gas out of the ground. That is what is known as hydraulic fracturing. There's other types of other types of formations going on in here. Sometimes it's what's called tight sand gas, where it's just gas in like sandstone. Sometimes there's oil, and you can even get methane from old coal beds even. That's more common in Australia though. This is, again, what hydraulic fracturing looks like in cross-section again. So there's a lot of activity at the surface where you have this wastewater getting developed, or wastewater getting, water getting delivered to the site that gets injected underground. It gets injected along with some explosives to crack the rock, and then it's injected with sand and these chemicals to basically prop the rocks open, prop the rock formation open, dissolve anything that needs to be dissolved. There's like antibiotics injected to kill methane digesting bacteria, pH adjusters, salinity adjusters, corrosion inhibitors. Like all kinds of fun stuff goes underground to make this well do what it has to do. And then the gas comes back out. With the gas, there's also potentially oil, water that you injected underground. That's called the flowback water. There's produced water, which is water that was already sitting in the formation in the first place. Sometimes it's radioactive, comes back above ground, and that gets collected, and then usually it has to go off to either some kind of temporary or permanent storage. Sometimes it's a pit near the site. Sometimes it's reusing an old oil well to just dump the wastewater after it's been used 5 or 6 times. This is another schematic of what that looks like that's more focused on where gas can go. So when you hear about sort of gas leaks or wells that have blowouts and that kinds of thing, most often it is cases of where this casing at the top here, so normally there's a cement barrier that's supposed to keep the gas out of the water and the water out of the gas. If that fails, that's the case in which most of the water contamination has happened, is where there's a failure of this contamination or a spill of like a truck or something at the surface. Cases where there's been like documented contamination through these fissures that are deep underground in the formation, those are like extremely rare. There's maybe been like 4 or 5. So just to talk through the definitions a little bit here. Hydraulic fracturing is this process of using fluids and explosives, fracture formation containing oil or gas. The oil boom in this country started in Pennsylvania, like 40 miles from where I grew up, if that. The second thing we figured out how to do after how to drill a well was how to drop explosives down into it. They're called oil boom towns for a reason. It's because of the explosives. So this idea of like drilling a hole in the ground and making it blow up is not new. Horizontal drilling, however, is a little bit trickier. That I don't think got developed really until the 60s and wasn't common until the 90s. And these high volume hydraulic fracturing wells, which is like the shale boom and what we usually call fracking wells, that really didn't get started until about 2008 when we figured out how to put explosives and drilling sideways together and do it in a way where you can actually make money. There's also this type of well called an acidizing well that's more common in California just because the rock formation is different, so you need different stuff to get the to get the oil out. This is again zooming on my hometown, just showing an overlap between 3 different shale formations here and the exact sort of prevalence of both these oil and gas wells. Again, the The blue ones are gas, the tan ones are oil, and in Pennsylvania, at least, some of the gas ones are old, some of them are hydraulically fractured, especially the bit that's in the bottom of the screen here, which is a bit east of Pittsburgh. Most of the ones the splotch of oil wells, like kind of on the Pennsylvania-New York border, is centered on where I grew up. It's mostly old oil, and kind of the north and west is a mixture of things. Most of that is conventional, though, until you go further west into Ohio. There's in this country, about 17.6 people that live within a mile of at least one well. This is where those people are. These counties are kind of highlighted based on how many wells are present in each county. So you can see that there are some places that have more than 5,000 wells and some that have only a handful. Of these wells, many of the wells that people are close to are actually conventional wells, so they're not doing hydraulic fracturing. They may also be old wells, especially in areas with legacy oil and gas production. But you can see there are a lot of people living near, or a high proportion of people living near unconventional ones in like Michigan, Arkansas, the Dakotas, and in Colorado, where there's a lot of new activity and not a lot of old activity. What people are living next to also varies quite a bit. It can be a mixture of oil, it can be dry gas, which is straight methane, or it can be wet gas, which is methane mixed with like propane, butane, and kind of higher order stuffs that can be used for the petrochemical industry, for plastics manufacturing, or for like butane, like in your kitchen torch. Ranges from places like Virginia, it's all dry gas, to places that are almost entirely oil, like California and North Dakota. This is going to be an animation, hopefully it works, of the growth in, there you go, the growth in unconventional wells. So again, these are deep, horizontal, and a large amount of fluid being injected underground. So you can see there's been that large explosion around Pittsburgh and in the northeast corner of the state, some of it extending into Ohio and West Virginia as well. I'll let that loop one more time. There's a lot drilled, especially in 2012 and 2013 and 2011. The drilling of new wells has tapered off a little bit since kind of hitting peak around 2011. But regardless, there's still a lot of wells there. It is a very underappreciated contributor to air pollution. It is the largest human-caused emitter of volatile organic compounds, which is a class of compounds that they happen to have carbon in them. Some of them are hazardous, some of them are carcinogenic, some of them contribute to ozone, and some of them contribute to particle formation. So it's not a great class of compounds to want to emit. And living in close proximity to one of these well sites has a whole slew of different exposures and health impacts associated with it. There's air and water pollution, ground pollution, noise, light pollution. There's been instances of asthma, nose, eye, throat irritation, headaches, fatigue, increased hospitalization rate, birth defects, childhood hematological cancer, and other health impacts that have been associated with living close to a well. That's near a well. Production also contributes a fair amount of air pollution to regional air pollution. So if you look at this map here, this is work that I'm working on. It's in progress now. This is showing the contribution to PM 2.5, which is one of the main regulated and main health harming air pollutants that we're worried about. There's a big hotspot in Colorado and a smaller one in North Dakota, but you can see that there's PM 2.5 getting to a lot of different locations where there's not a lot of oil and gas activity, like say Missouri, Illinois, Massachusetts, Iowa, and places like that. And it gets even more apparent if you look at the contribution to ozone, where it's basically everywhere that's downwind of oil and gas is getting hit with some ozone coming from oil and gas production. And when we run that through our health impact assessment models using what we know about exposure to PM 2.5 and ozone, we find that there's about 2,500 deaths attributable to oil and gas production in 2016 alone. doing some work right now that's going to incorporate the ozone epidemiology, and when that happens, this will go a little bit closer to 5,000. So 5,000 deaths a year due to air pollution from oil and gas. So that's the air pollution. There's a lot going on underground as well, but it turns out we don't know as much as we could because 20% of the ingredients that get injected underground and then the hydraulic fracturing fluid are not disclosed. So it's really hard to assess the health impacts of something when you don't know what it is. It clearly varies by state. What is and isn't disclosed, but by and large, it's close to 19%. We do know that there are a lot of different chemicals used in different processes throughout hydraulic fracturing. It's a pretty complicated process to build one of these wells, so there's a lot of different fluids that get used in different steps. There's the drilling fluid that's used to lubricate the drill bit, which is different from the hydraulic fracturing process, which is different from some of the other well treatments you would do, which is also different from acidizing, which is again more common in California. But there's a lot of different chemicals that get used kind of across the spectrum here. And some of them are very specific to specific processes and specific types of wells, which makes it very difficult to kind of generalize anything. Going through this assessment, looking at these many compounds, there's at least 17 that are acute mammalian toxins, which means they will produce severe health impacts quickly if you're exposed to enough of them. These are notable things you probably haven't seen since your organic chemistry class, like propargyl alcohol, hydrofluoric acid, formaldehyde, glutaraldehyde, and butoxyethanol. A lot of these very common. Here's some of the most common chemicals that are used. They do have known health impacts already. Toxic to kidney and liver, the renal and hepatotoxicity. Trimethylbenzene makes you less sensitive to pain. Naphthalene affects body weight. Sodium chloride affects neurodevelopmental effects. Formic acid is a reproductive toxin. There's all kinds of stuff you don't want to be exposed to that's being injected into these wells. Possibly more terrifying than that is that there's a lot of different developmental and reproductive toxins, and of a total of 1,000 substances that were being injected underground, there were 781 for which there was no information available. So again, it's hard to know if you're being harmed or not when you don't even know what you're being exposed to. Of the 240 where you did have information available, for many of them, the kind of weight of evidence was very unclear, but most of them tilted toward having some sort of health impact rather than not. And I want to remind people that, so this is getting injected underground. It will usually come back along with whatever's been pre-existing in the formation, which is usually heavy metals or chemicals you'd see associated with oil. And again, that has to get disposed somewhere. Again, wastewater disposal wells. So this here is a map of where the wastewater disposal wells are in California. And this is where the farming is. So if you just take a look at the map, you will notice that, yes, there is wastewater being injected very close to where a vast majority of a lot of this nation's fruits and vegetables come from. And because there's a bit of a water shortage, some of the oil companies have gone so far as to kind of brand themselves as a combined oil and water company, where they will just drill underground, take what comes out, and sell you both the water and the oil separately. The regulations arguably aren't kind of up to snuff as far as detecting. I mean, they meet the regulations, but the regulations don't cover a lot of the chemicals that are exposed to oil, so it's hard to break the law when the law you might be breaking doesn't exist. One other great thing you can do with this wastewater is put it on your roads. When I was home for 4th of July, this was literally the front page headline, was an argument about the Pennsylvania Assembly deciding whether or not to spray oil wastewater on roads for ice control and for dust control. So that's what we know about the production side of it. There's still 2 parts of this left. Midstream. This is everything that goes basically from the extraction area to get to your local gas company or your power plant. This is what the midstream infrastructure looks like. Again, every single one of these lines is a pipeline, a railroad, pipeline or a railroad. The blue squares are the processing facilities. The white squares are all the storage facilities. And the triangles are all the different petroleum terminals where oil products are stored. So remember what I said about the 10 or 20 of these, 10 or 20% of the gas gets stored underground. This is where those facilities are. Many of them are in sort of around Ohio, Pennsylvania, and West Virginia, and Western New York. There's a lot in Michigan, and most of those are in old oil wells. There's many in Illinois that are stored in old aquifers, and a few in California that are again stored in old oil fields. Many of these wells are extremely old. This is from a paper that we did 2 or 3 years ago where we tried to figure out how many other Aliso Canyon style wells there are out there. And it turned out that there were about 2,700 by our estimates. So these are wells that are too old to really have good concrete and casing done. They were previously oil wells, so they're not designed for the levels of pressure you get with gas, and they're placed in old oil fields. So using those 3 criteria, we found 2,700. There's probably more since it was conservative, our methods. And again, most of these are clustered in Appalachia and Michigan. So some of these are in areas where there's no people. Some of these are literally in the middle of suburban neighborhoods. So this is a map of a piece of Stark County, Ohio. Every single one of those circles is a, every single one of those circles is kind of a 200 meters, so that's approximately 600 feet buffer area around a well, and every single gray spot is a house. So there's a lot of wells that are very close to a lot of houses, but it really varies. You can get a lot of different exposure to who is extremely close to these wells based on how you count it, which is kind of was the point of this figure here. But there's 2 different methods to estimate that. This is just comparing the 2, but more to the point is that there's a lot of people living very close to these wells and may not know it. So that's midstream. We don't know a lot about pipelines because it's a lot easier to figure out where these are than it is to figure out exactly where the pipelines are. And then this is the end part, which is consumption in industry, in buildings, and in power plants. This is what consumption looks like. The blue circles are gas-fired power plants, the brown ones are oil, and the color coding I have in here is population density. So it's consumed in cities where people are for heating. I'm gonna zoom in particular on this bit for just a second here. I know some of you have probably heard of gas leaks and have been worried about them. There's a lot of them, especially in Boston, New York, DC, Philadelphia, any old city that still has cast iron or even like wood pipes underground. So you've seen kind of the path that gas can take going from well to your stove. And you might be asking yourself, what is in the gas? There's a lot of things that you would expect, which is usually 95% methane, 1 to 5% ethane, propane, butane, these other higher order alkanes, sometimes making up like kind of close to 1% maybe. And a lot of things that you wouldn't expect, like benzene, toluene, ethylene, xylene. These things are toxic, carcinogenic, and regulated. There's also a lot of other complex volatile organic compounds, which again looks like an organic chemistry class. So trimethylbenzene, ethyltoluene, tetrahydrofuran. Again, hazardous, carcinogenic, toxic compounds that you probably don't want to be exposed to. And turns out there might be some of these in your gas. So thinking through what people are getting exposed to, kind of the number 1 and 2 questions you ask yourself is, do you have a gas leak? So you could be exposed from a gas leak anywhere from sort of your sidewalk, walking down the street if you smell gas, all the way up to the point of where you combust it at your stove. But at your stove, there, hopefully most of this is burnt. So if you're breathing in fumes from an active gas fire, you're probably just breathing in mostly NOx and PM2.5, which those at least we know are toxic and know precisely how toxic they are. Now zooming back to the rest of consumption. And one of the things that you'll say, you hear a lot is, this, as I alluded to, like a lot of gases displacing coal, and a lot of people are probably saying, but gas is better than coal, so why are we worried about it? Which is kind of reasonable. I mean, e-cigarettes is probably better than normal cigarettes. But the impact of these things is definitely going down over time. This is from some work that I'm working on. It's funded by RMI and Bloomberg. Just looking at PM 2.5, you can see that there we go. The impacts of coal are going down quite a bit, and gas has stayed more or less steady. So we might, looking at one aspect of the health impacts, we may have gotten to the point where gas is possibly worse than coal. We are still working on that at the moment. Jury is still out. This doesn't include ozone. This doesn't include NO2. This doesn't include what people who live near power plants or whatever else are being exposed to. This doesn't include methane leakage, and this doesn't include other life cycle impacts. It's just looking at one aspect of the pollution that's coming out of power plants. There are questions about the greenhouse gas emissions as well. And it really depends on what time frame you care about and how much leakage there is across the life cycle. So if you're worried about a 100-year time horizon, and you're worried about sort of national average leakage, gas is better than coal as long as the methane leakage is below 3.2%, which basically we're pretty close to, and maybe a tiny bit under. So maybe we're doing okay-ish, but it really varies depending on where you are and where your gas comes from. From some fields in like the Marcellus, it could be the case that the methane leakage is fairly well controlled. But on the other hand, if you look at a place like the Permian, there's a large methane anomaly there. And based on some monitoring that's been going on in the area, this group published a paper showing that the methane leakage rate is 3.7%. So at least in this region, the gas is worse than coal. The last point that you'll hear about is, what about jobs? This other great paper, they did some work looking at the air pollution health impacts here. So on the left side is the air pollution emissions broken out by source along the supply chain, all the way from like clearing the land for the well all the way to burning it in your power plant or your stove or wherever. The emissions are largely in the areas where you'd expect. The premature mortality was largely happening in places downwind because air pollution travels. And there was a fair amount of it. But more to the point, this paper also looked at the employment. And well, they did find that there was a fair amount of employment coming from the natural gas industry. It was largely in the areas where there was some extraction happening. And again, it kind of varied depending on where you are. And about a third of it was direct employment by the oil or gas industry, and 2/3 of it was a supposed like spillover effect. So this group took it upon themselves to compare the two. And basically they found that if you comparing the employment benefits versus the air pollution benefits, for every 217 job years, so that's maybe about like, what was the math on this? I did this in my head. 5 or 6 people being employed, you have 1 death. For every 3 years a person is employed, you have 1 year of life lost. And there are some kind of reverse equity concerns here, where most of the benefit is happening in Western Pennsylvania, Eastern Ohio, West Virginia, and the harm is usually happening in cities that are usually downwind of the areas producing. So it's a very bizarre kind of equity thing, where it is benefiting the areas that are experiencing, benefiting the areas where there is extraction happening, and kind of exporting the harm to people living downwind. Some of them are us. And for my last bit here, there's this process, kind of scientific process, EPA and other kind of governmental agencies go through this, called risk assessment. It's a 4-step kind of process where you look at any kind of hazard or any pollutant to say, does it look like there might be health problems? You then go through and figure out the dose response. So if I'm exposed to X amount of thing, how much health impact is there? kind of in parallel with that, if you're evaluating something in the real world, you want to figure out what people are getting exposed to. And you put those two ingredients together to get a sense of like quantification of the risk. So I'm going to put it together like this. You have this nice diamond here. Hazard identification in yellow, the exposure response in this exposure response assessment I'm calling it here because we often don't know what people are being exposed to in this fuchsia color. Blue is the exposure assessment and green is the risk characterization. And I'm going to end by saying, oops, that was too fast. Everything that we know is, sorry, it's the literal end of my thing, so it's dying. Basically, everything that's filled in is things we know, everything that's in white is an evidence gap. So you can see there's a lot of hazards that have been identified and a severe lack of information on most of these things. And with that, I'm gonna double check and make sure that my correct screen is being shared so everybody can see that lovely diagram. It is a work in progress. I had this idea like 3 hours ago. If you talk to me now about any one of these specific nodes, you can probably change my mind about something. But I think this is a good way to very quickly demonstrate that we do not know what's going on. And working in this industry, or working on this industry for some years, the evidence gaps are things that we know are missing. So every 5 minutes, there's like a new surprise. I'm gonna stop there and take questions, comments, whatever else. Thank you.
Thank
And a
you,
drink of water.
Jonathan. That was amazing.
Yeah, thank you, Jonathan.
You're welcome.
That was incredible. I just learned an incredible amount. And
I will send the slides after.
Okay, it's beautifully clear. What questions or comments do people have? We can just have a conversation at this point, so you can unmute yourself and talk.
Hi, this is Claire. Hi, I wanted to say thank you so much for that great presentation, Jonathan.
And Claire, you might want to get a little closer to your phone. It's hard to hear.
I'm sorry. Okay, I think I had my finger over the thing.
Okay.
Thank you. That was great. I also learned a lot. I'm still sort of reeling, trying to process everything because it was a lot of information, but was beautifully presented. I'm just curious, when you talk about air pollution, you're talking about air pollution from the combustion of the gas and not from the extraction or associated leaks or carbon emissions. I mean, air pollution is just kind of a bucket. So I'm just wondering what is in that particular bucket. Thank you.
Yeah, like it depends on which piece you're looking at. So in this group study, it's anything related to anything across that life cycle that happens to result in producing PM 2.5 in the very end. So it's not fairly narrow in that aspect. So it doesn't include ozone, doesn't include benzene people are getting exposed to close to the source. It exclusively looks at emissions that will eventually lead to PM 2.5. So that's NOx, PM 2.5 being primarily emitted usually basically as dust. These volatile organic compounds, and exclusively if they go on to do chemical reactions that form PM 2.5, and trace amounts of a couple other things that will go on to form PM 2.5. So sulfur, direct NO2 itself, benzene, toluene, xylene, all the other things, ozone, which is a big one, all missing. And that one is looking across the life cycle. This one is just looking at combustion, unfortunately, but again, I don't have tons of tools available to me or an army of students, so I kind of got to work with what's cheap and easy. And sorry to be giving people like epilepsy here. This is looking at both things that contribute to PM 2.5 and to ozone. So it's including a lot of formation of compounds from those VOCs. But again, the close range health impacts, if you're living like a half mile from a well, not included here. And combustion not included here. This is just everything from the wellhead to like the major gathering pipeline that happens to produce PM 2.5 and ozone. And we know a lot about how it affects health. That's it.
Oh, I had a couple of questions. One is if you had any comments on, just with all your knowledge and expertise, about the Weymouth compressor situation. And also, I don't know if you could explain what PM 2.5 is exactly.
Okay. I'll start with PM 2.5. It is literally any particle that's basically, you can fit at least 20 of them across the width of a human hair. So they're quite small. And because they're that small, we're worried about them because they can travel a fairly long distance. So they're too large for like the normal molecular motion, Brownian motion, to like cause them to like bump up against things and get stuck. But they're too small for gravity to pull them out of the ground or pull them to the ground. So they just stay in the air for usually like 1 or 2 weeks. And because they're so small, they're also able to get deep into your lung. And once they get in there, they're also small enough to cross the barrier into your bloodstream. And once they're in your bloodstream, they can get basically anywhere. And the list of health impacts that have been associated with air pollution is probably at this point higher than the list of impacts that are definitely not associated. So like basically anything being related to PM 2.5 is on the table. For the Weymouth compressor station, I commented on the HIA, provided some information to somebody, and wrote a grant to do, the health impact assessment, and wrote a grant to try to do more that got rejected.
And in terms of your perception of risk for the Weymouth compressor station, I'm just kind of extending his question for a second, or her question.
Yeah.
Relative to some of the other things you're discussing with the new compressor station, what are you most concerned about in terms of impact to the community?
I mean, it got permitted. Like something happened last week, like FERC approved it or something.
Yeah, it's turning on tomorrow.
All right. Yeah, I mean, this is one of these, so, yeah, we just, like, very little is known about what you'd get exposed to near one of these things. I mean, again, knowing what's in gas, there's a lot of things. There's combustion on site. It's hard to know what to be worried about because there's so many things about living near a compressor station that we don't know. I don't have it on here, but it'd be, I guess, kind of, yeah, there's the yellow dot. We know there's a hazard. We don't know what people are being exposed to. And if we don't know what people are being exposed to, we can't know how they're going to respond to it. So we can't know how bad it's going to be. But, I mean, I'd be worried about, for chronic exposures, if it's a compressor station, there's some kind of fuel combustion on site. So there's the usual suspects of NOx, PM 2.5, formaldehyde, maybe some sulfur. And if the thing isn't working perfectly, there might be some leakage of gas, which means whatever is in the gas, people are being exposed to. That would be sort of low-grade chronic exposure while everything is working properly. To the best of my understanding, it's not the least flood-prone site in the state of Massachusetts. So there's a better chance of it getting flooded than if it were placed in like Worcester or, a mile west or wherever. So, if there were a hurricane, a flood or something, something could go wrong and people could be exposed to more than just low-grade formaldehyde and hydrogen sulfide.
Thank you.
You're welcome. But it's hard to know what people are being exposed to because we don't know what's there.
Yet.
Yeah.
Other question?
Go ahead.
This is Claire again. I was just wondering if you could talk a little bit about your collaboration with HEAT. I am a big fan of HEAT, and I know you guys have worked together in the past, and I know that you probably have some things cooking on the back burner. So if you could share a little bit about what is going on with your sort of intersection of your interests, I'd love to hear about it.
Yeah, there's nothing cooking on the back burner because we took that gas and we sent it to a lab to be sampled. So yeah, that's what we're doing. It had to be on pause for a little bit because of that whole pandemic thing. But we have been sampling gas in people's homes. We've been getting it sent to labs to figure out how much of what is in it. And we're going to try and produce some, scientific evidence to demonstrate that it's not just methane and ethane that's in this gas, and there are some things that are fairly hazardous and possibly regulatable if we can show that there's enough in it. So when Gina McCarthy, who used to run the center before she became head of the board of advisors and went to go be head of the NRDC, she was really excited about this because if we can show that there's some of these chemicals in gas, benzene, toluene, ethylene, xylene, and if we can put a number on how much gas is leaking from pipes in Boston, there's certain regulatory thresholds that could be crossed that will set into place some EPA rules that will force these emissions to be regulated under the Clean Air Act. There's a lot of evidence that needs to be compiled and a lot of science that needs to get done before we're there, but this is hopefully the first step of many toward kind of demonstrating whether that's true. And well, demonstrating whether we're across that threshold or not.
Nancy, you're muted. You want to unmute?
Yeah, no, I just wanted to know if I could go next. Did you want to finish on the what you were just talking about? Because it's an important point. I'm glad Gina recognized that. It seems like that is a very nice hook in terms of getting some regulation. But I was going to go in a different direction. So if you want to finish that's
no, that's the end of it. Yeah, if there's regulation in place, suddenly there's a lot of regulations that kick in that can require these emissions to be controlled.
Yeah, no, I think that's a really important point, and I hadn't thought of that. Just like Gina, new angle, new way to go. I had heard and I had read some about the water chemicals and how unregulated they were, and that nobody knew what they were. So this was very helpful to me in terms of putting some concrete, if you will, evidence on that. And I think that's something people would be very interested in hearing more about. That would be something to make the public aware of. I think that resonates with people when they hear that their water's being contaminated for whatever reason. Sometimes it matters more than air. I've never, working on air quality all these years, I've never understood that, but it seems to be true. But my question, Jonathan, was, I know those chemicals are used to get the fracking started. Do they have to continue to use water, or is it the kind of thing that once the area has been fracked, if you will, then the water and the chemical use backs off? So is it a long-term continuous thing, or is it an initial slug and then fortunately it's backed off? I don't want to minimize it, but I just want to know if it's an ongoing issue in terms of water use and chemicals, or a short-term thing.
It's a good question. And again, it's hard to know because, there's not a lot of sampling and monitoring before and after these wells. So there's there's chemicals that you intend to inject underground, and then there's sort of water pre-existing in the formation that's essentially been contaminated by the shale. So a lot of these shales, the shale formations, they have heavy metals in them. There's polycyclic aromatic hydrocarbons in there, many of which are carcinogenic, and all kinds of other fun stuff in the formation. So when you do the injection, you mix everything, and then it comes back up out of the ground. Sometimes a lot of it is left behind. Sometimes a little bit of it is left behind. It depends on the geology, it depends on the pressure, it depends on the drilling operator, and like all kinds of things that makes those very potentially well to well, let alone like state to state. And then this water has to be disposed of somewhere. Usually it's disposed of in old wells again. So in some cases, there could be some wells where it just happens to be that maybe they're under a lot of pressure, so like all of the fluid comes out. And there's other wells where maybe they're under low pressure and like 90% of the fluid that went in doesn't come back out. And if you live next to one of these wastewater disposal wells, like you're on the receiving end of 6 wells worth of contaminants where like they're being injected underground with the intent of them not going anywhere ever again. And nobody really knows, like, it took a while for me to figure out where this is one of the cases where I had a student who went through and was able to make a map of where some of the wells are. Her data is now out of date. And again, because we applied for a grant, didn't get it, and now we can't do the research we intended to tell people like, oh, you're living next to a wastewater well. It's just kind of sitting on a hard drive, like going out of date as we speak.
Jonathan?
Yeah.
I was gonna ask you a question about funding, but I'll look on that for a second. And when we went down to visit the frack pads in Pennsylvania, we talked to a lot of people. We just randomly went and talked to truckers and so on. And my understanding was that in one drill site, one frack pad, that they actually do the fracking process many times, and like they do a single fracking job with the pressure, and then they send down this plug that plugs the system, and then they do the next frack job. And so each time they have a new set of fracking fluids with the added chemicals. So I think that's one other piece of information that you're going to get. And I can't remember the number, but it was shockingly high how many times they would do one site. Do you remember, Audrey?
Yeah.
I thought it was 200, but it could be my bad memory.
Yeah. I mean, it sounds, anything is plausible. And with a lot of these well paths, like the schematic I showed was just like the one down and then one path sideways. Like sometimes like looking at a picture that I don't have access to anymore because we lost our subscription. You used to be able to see like where the path of all these different drilling pads or the well pads go. So sometimes you can have like one sort of kickoff point, and then there's like 6 or 8 wells going out in like a little flower formation. For some wells, like maybe there's oil or gas at like 2 or 3 different depths. So there's like 3 different kind of break points where it goes sideways. Yeah, there's a lot of very kind of astounding engineering that goes into these, and like there's all kinds of stuff that happens on site.
And then the other thing I wanted to add is that one of our other collaborators, Archana Dayalu, she is a co-author on a publication that makes the frack focused database publicly available, which is a list which might interest you, Nancy. It's a list of the chemicals that are recorded, not the 18% that Jonathan mentioned that we don't know, because they're quote proprietary. Right. Thank you, Dick Cheney. Yeah. But the rest of them, so you can look up.
Yeah, I pulled the not disclosed from her paper and left the disclosed behind.
Awesome. So my question was about funding and how we solve the funding problem.
Yeah, so the way that it is right now is the center runs 100% off of grants. Since we're doing environmental health research, there's no profit going to the university. And the university doesn't really provide us any like financial support, and actually expects us to pay overhead to help Harvard pay rent, library subscriptions, like all the things that go into running a university. So we don't have a lot of support, and it ends up being very tricky to do this kind of work. Basically everything is done off of a shoestring budget, and almost entirely run by foundations, almost entirely funded by foundations. And so because of that, and because there's sort of ebbs and flows with funding, it's very hard to kind of keep myself funded, let alone like hire students or people to help with research so we can have a steady stream of things. So yeah, so it ends up being very tricky, and the way to solve it would be to have a large, many-year, like substantial chunk of funding that can be used basically at our discretion. Another problem that we run into is that, you know, there'll be some interesting law, and 3 months after this policy opportunity happens, a funder gets interested. We have to then write a grant, get the grant approved. That takes 3 to 6 months, and then start the work. So by the time a window arises, we're already at least 9 months behind. And I mean, we've been late to a lot of parties because of it. And I think a lot of environmental progress has not happened because we haven't been able to do anything in time because we don't have discretionary money to spend. So I think if that problem were to be solved, I think a lot more policy relevant work can be done.
So I just still remember sitting around the table with a bunch of people, and I think, I can't remember which person, it